Welcome back. So, in our last class I mentioned that today we will start something important which is called metric space or metric. But before that we need to know what is the metric and how it is related to function and vector and all these things. So, essentially metric is defined by a pair. It is a pair, say chi and d, but this chi is the space. It may be a vector space or the function space, and d is something called metric. D is something called metric. So, two things: one, it is a pair and it defined over a space. So, metric, whatever the d I mentioned here, it defined over a space and we called it as a metric, but I did not define so far what is the meaning of d. So, now d is called metric when they are following 4 properties. D is following 4 properties. What are they? So, let me write d alpha beta, it is always greater than equal to 0. When alpha beta belongs to the space, whatever the space I am talking about. So, this is, if this is a vector space, alpha beta are 2 vectors. D is something which is related to this alpha beta in such a way that it should be greater than equal to 0. How it is related, so far I do not know, but I am saying that d should be related over alpha beta in such a way that it is greater than 0. This is the first property. Second property, that d alpha beta and d beta alpha are same. That means, if I interchange whatever the operation I like to make through d, if I interchange alpha beta, there will be no change. That means, alpha beta, whatever the value I have, if I do the same operation with beta alpha, I will have the same thing. D alpha alpha is equal to 0. Please remember that in the first case I said it is greater than equal to 0. Now, there is a possibility that beta be equal to alpha. This is arbitrary vectors, but I am not saying that alpha is not equal to beta. There is a possibility that alpha may be equal to beta. If that is the case, then this quantity, whatever the quantity I define as metric, should be 0 or vanish. And d alpha beta, this quantity should be less than equal to d of alpha gamma plus d of beta gamma, when alpha beta gamma belongs to this quantity. I can take an additional quantity and I can say that whatever the metric I will have with alpha beta by operating these things, and if I conjugate, if I make a relationship, this metric relationship with another element gamma with alpha gamma, and that will be associated with beta also with this, and then take 2 metric and add this to these 2 things, and I am getting something which will be always greater than equal to my original metric d. So, these are the definitions. So, it may be confusing for you, what is the meaning of these things, you may not understand clearly, but let me say that in R2, in R I define metric dxy, I define dxy is nothing but mod of x minus y, when x and y belongs to the real number. Whatever the real number you can take, if I take x and y, if I take a mod of that, it will be always greater than equal to 0. First thing is valid. Second thing is that if I interchange, if I write x here and y here and x here, it is not going to change anything. The value should be same. This is same as y minus x mod. So, second thing is also valid. Third thing I am saying that when the two things are equal, then it will be 0. So, if I take x both the cases or y both the cases, readily I find that the d which is defined like this, that is the distance between two point in real axis here, if it is x and if it is y, distance between these two things, not only distance but mod of the distance, the magnitude of that thing, not the only the numeric value. Then when x is y equal to y, x is y, then do these two things are same, then I will have 0, no doubt about that. And in between, if I put something here, in this case z, so I can readily say that these things will also follow. And here, since it is falling in the same line, so I can have dxy, which is mod of x minus y, which will be equal to these things. But here you look that it is never said that it will be always greater than equal to, but it is less than equal to this quantity. So, that means the equal to sign is there. So, it is valid, still it is valid, since it is following in the same line. You can also define in R2 the matrix like this way. So, here I need to write say x1 y1 to quantity and x2 y2 another point. If I define these things into this way, x2 minus x1 square plus y2 minus y1 square, then this quantity also can be considered as a metric. This is nothing but the distance between 2 points in Euclidean plane. So, I have one point here x1 y1, I have one point here x2 y2. So, in Euclidean plane this is the distance between these two, and if I calculate the distance between these two by applying the Pythagoras theorem, then readily I can have this equation in my hand. So, this is the distance. Now, I am saying that this is nothing but the metric. So, distance between 2 points is nothing but the metric of this particular space. Say it is a 2-dimensional vector space. So, 2-dimensional vector space also I can define in this way. This is always followed, this is always followed. If I interchange, no problem with that. This thing is also followed. If this point collapses to this point, so distance between 2 points which are same is 0, and this is nothing but another point. If I put any another point here which is x3 y3, so it follows the standard triangular rule that if this triangle is there, I have a distance this a b c. So, AC, this is the standard triangular inequality, AC will be always less than equal to AB plus BC, where AC is a distance, this is a quantity, this is not a direction. In vector they are same, but here I am taking the root over of that, that means AB is nothing but the distance. So, length is always these things. So, it is followed by this. So, that means I can define my metric in R3, R2, R1, Rn according to my choice. Only thing is that they need to follow these four criteria which I have written here. Okay, now in function space also I can define something like metric. So, in metric in function space. So, metric in function space. In function space, how I define a matrix? For example, two functions f and g, which belongs to the continuous function set of continuous function in the interval a b. These are the two functions are given. Then I define the matrix D as of f g as maxima of f minus g. So, I have a function f, I have a function g, f minus g will give me another function, take the mod of that function, then the maxima. If I define my D in such a way that I can find that this is following all the 4 rules. Quickly, let us check quickly. So, two functions a and b, one function, say this is my f and this is my g. So, if I draw f minus g, then I will have something negative here, and then at this point two function crossover. So, I will have a 0 here, and then it will be something like this. So, it is f minus g I am plotting. Okay. Now, what the definition suggests, I need to plot the mod of that thing and maxima. So, mod of that thing if I plot, then what happened, these negative things will flip and go to the upper side, because I am plotting the mod of these things. So, it will flip and go to the upper side, fine. When it flip and go to the upper side, then I will have this functional set which is never negative, maybe it is 0, but never negative, and then I say it is maxima. I am trying to find out the maxima, that means at this point it is a maxima. So, this is say maxima of f minus g. Now, this is my metric. Now, you can readily find that this quantity is always greater than equal to 0. It at most 0, but it should be always greater than 0, because I am taking the mod of that. If I interchange f and g, there will be no problem, because whatever you do that, if f minus g and g minus f will be same, because you are taking the mod sign. So, mod sign will take care of. If both the functions are same, alpha alpha, so that means instead of putting h, if I put z, then what happened, the function will be subtracted from the same function. So, I will have entirely something 0. So, maxima of 0 will be maxima will be 0. So, this quantity will again be 0, and again if I put some another quantity, say another function h. So, I can write this this quantity, say maxima of f minus g, that will be always be greater than of maxima. So, how let me do that in more critical, more general way. So, f minus g mod, I write it as f minus h plus h minus g, right. So, mod of a plus b, should be less than equal to this quantity I can write from here to here. If I write here, then I can take from this equation, I can take the maxima will not going to change, f minus g is equal to less than maxima of f minus h plus maxima of g minus h. This is my definition, this is f g. My definition, it is this quantity, and my definition, it is this quantity. So, these things and these things are same. So, that means in function space also we can define something which is behave like a metric, and these are the four properties that should follow by this metric. So, you can define by your own way, but the only condition is that this 4 quantity should be satisfied by this metric whatever you define. Okay. Now, we will go to more important things after having a brief idea of what is the metric and how it works in function or vector space. Now, we go back to something important, which is linearly dependent and independent function. So far we are dealing with something linearly independent and independent vector. Now, I am saying that I am doing the same thing, but here instead of vector I am saying that linearly dependent and independent functions. By definition both the things are same, the definition is exactly same. What is the definition? So, for vector, if you remember the vector, so let me start with the vector E1, E2, En is a set of n vectors, this is for vectors. They are linearly independent if I have this equation has a trivial solution, only solution C1 is equal to C2, Cn is equal to 0. If we have the only solution that these are the 0, then I can say that then my conclusion was, it is just a recapitulation of what is linearly dependent and independent vectors are linearly independent vectors. Okay, this same thing I just rewrite once again. Now, I will say I will define what happened in case of linearly dependent independent functions. So, let phi 1 x, phi 2 x, phi n x are set of functions. All these phi i's belongs to the continuous set of continuous functions. This is a subset of continuous functions, and this subset of continuous functions means all are continuous in the regime A and B. So, these are the functions, set of functions I have. Now, if this is 0, then if the only solution C1 is equal to C2 is equal to Cn is equal to 0, I say this is equal to 0, and I am saying that the only solution for that is equal to 0. Then we can say the set of functions phi I x are linearly independent set of functions. So, the by definition this is exactly the same that we have in the vector space. In the vector space I have few vectors, set of vectors, and then I make a linear combination of this set of vectors with C1, C2, C3 the coefficient. Here I am doing the same thing. I have some functions in my hand, the set of functions. I am making a linear combination of this set of functions. When I make a linear combination of this set of functions and I am saying that the linear combination give me something 0, then I am saying that when they are 0, then the only possible solutions and only solution is all the Ci's are 0, then readily I can say that these functions are linearly independent set of functions. By definition, the linearly independent set of functions and linearly set of independent vectors are exactly the same, but the question is here how to find out a set of function is linearly independent or not. That is a more important question. If a set of function is given to you, how you figure out whether they are linearly independent or not. Okay. So, let us take phi 1 x, phi 2 x, phi 1 x is given. I need to find out whether these are the linearly set of independent functions or not. So, I start with this equation phi 1 x plus phi 2 x this is my equation 1. So, I start with this equation. Next what I will do, I will take a derivative of this equation both the side. So, C1 phi 1 x derivative means the standard derivative, there is no other things. First derivative I have another equation, equation 2 in my hand. I will do again, I will do one derivative. This suggests that the order of derivative, this is the second derivative, this is the first time I am making the derivative, this is the second derivative, and so on. If I do up to n minus 1, then I will be ended with this equation. Okay. So, this is a set of equations, n number of equations in my hand. If I write this n number of equation in matrix form, then how it look like? This is nothing but a homogeneous equation. This equation I already shown in previous lecture, that I can write in this. So, C this multiplied by C1, this multiplied by C2 and so on, and I can write this. So, now I have a set of equations with this form, homogeneous form. So, in order to have a non-trivial solution, what I will get? So, we know that from this, if I write this in this way, so for trivial, for homogeneous equation, for trivial solution, for trivial solution, I write this entire thing in a matrix form. So, say okay, let me write in once again. So, A, this is A and this is C. So, A into C is equal to 0, this is a matrix form equation, and in order to find the non-trivial solutions of A, I should have date of these things. When this is equal to 0, then I will have a non-trivial solution. Then we will have the non-trivial solution. But if date of A is not equal to 0, this quantity is not equal to 0, then we will have, if this is not equal to 0, then we will have the trivial solution. That means trivial solution means all the C's are 0, the only solution. So, what I need to find out, that I need to find out determinant of this quantity. If the determinant of this quantity is not equal to 0, readily I can say that the functions are linearly independent. There is a special name of determinant of this matrix, whatever the matrix I form. This is called Wronskian. Defined is as W. So, W is this quantity, this is called the Wronskian. So, first if a set of functions is given to us, then what we will do, we will form the Wronskian of this set of functions. So, this is the Wronskian. First I write the function, then the corresponding derivative, first derivative, and so on, the nth order derivative. If the number of function is n, I need to go to n number of derivatives. So, after doing the n number of derivatives, if I put this function in whatever the result I have, if we put these things in this way, so determinant of this quantity is called the Wronskian. If this Wronskian is not equal to 0, I can calculate that easily whether this is not equal to 0 or not. Then the set of vectors, set of functions here, rather I should not say it is a vector, anyway they can, this set of functions are linearly independent to each other. So, that means if a set of function is given to us, so what we need to do is essentially find out the Wronskian, calculate the determinant, and if by calculating the determinant I find out the Wronskian, if the Wronskian is equal to 0, then readily I am saying that these functions are somehow dependent to each other. If it is not equal to 0, then I say that is these functions are linearly independent. So, with that I would like to conclude. So, I will start in the next class with some real examples to understand how a set of function be linearly independent and through which you can find it is a linearly independent or not. Apart from that, I will also like to mention another way to find out whether they are linearly independent or not. This is some sort of tricky, but still we can find, and this is called, the process is almost the same. This process, that process is called the Gramian method or Gramian determinant method. We will also learn that in the next class. So, with that let me conclude here. In the next class we will start with this Wronskian process, and try to find out if a set of function is given to us, whether how to find out whether they are linearly dependent or not. So, with that see you in the next class. Thanks.